present. If Sibo, if you can stop sharing, Sina should be able to share their screen. The talk of Sina is semantic optimal robot navigation using building information on construction sites. Oh yeah, I remember this paper. I'm not sure where you're based, Sina, but good afternoon or welcome today to ISARC and to this plenary presentation. I see you're able to share your screen, so I'm very happy. Oh yes, from Canada. I do remember now. So good morning to you then. And I look forward to your presentation. Thank you.
Thank you so much, Frederick. Hi, everyone. I'm Sina Karimi. I'm presenting this paper on behalf of all the authors of the Semantic optimal robot navigation using building information on construction sites. So as a bit of background and introduction, conventional methods of data collection rely on periodic observations. They are basically manual, which are textual data, and a limited number of photos. And these conventional methods are mainly subjective. So it means that the task of data collection relies on individuals' interpretation of the construction progress, so that they, when they go, they rely on their own interpretations. So we wanted to have this task automated so that we can provide more value to the construction industry with using a rover on the construction site. As you know, drones are being widely used for outdoor navigation, but due to their limitedness in indoor navigation, we use the rover for the task of data collection. As you know, it's a growing need in the construction industry for having the data collection task automated. And also by using different sensors and a robot, we can provide new kinds of information application for the construction stakeholders. And this method of data collection can provide accurate and reliable data for the construction stakeholders, which they can develop more applications such as progress monitoring and quality control during and after construction phase. So in this paper, we have three contributions. The first contribution is an optimal high-level path planner, which is based on BIM information, which is integrated with the low-level navigation. And they together create a cascade navigation stack so that the robot can understand the environment around it and do the data collection autonomously. The second contribution is the semantic teleoperation and navigation for autonomous unmanned ground vehicle, also known as rover, during the construction process. Practical implementation of the proposed system, which we deployed it on an actual construction site, is the third contribution of this paper. So to provide you a bit of background about how we provided all this information to the robot, I would like to introduce you to Building Information Robotics System, also known as BIRS, which is a previously published paper of the authors. So in this case, we use an ontology. We use two ontologies from the robotic domain to bridge the gap between the robotic domain and the construction domains, so that we gather all the information from CORA and MDR, which are two well-established ontologies developed by IEEE, and then we extend our building information robotics system. And now, after that, we provide the information from interoperable data from the construction industry, such as BIM and GIS. In this case, we are using IFC and SETI-GML as the interoperable data formats for these two technologies to bridge the gap between construction and robotic domains. And after that, we developed a topological semantics, and this topological map contains BIM and also GIS information that provides all the information to the robot. The first segment that you see here is the BIRS ontology. Then we developed a query that can reach out to that topological semantics, extract all the necessary information for the robots, and store them in the BIRS node inside the robot operating system. And by having all the information from BIM, and the navigation stacks, including sensors of the robot. We integrated BIM and ROS together to provide a platform for data exchange between the robot and BIM. And in this case, the robot has a very good understanding of the BIM environment during the construction phase, so that whenever the robot is in the construction site, it can understand where it is, what kind of semantic information is provided, as well as the geometry material, that everything is needed for data collection and also the robot's navigation. And the whole system provides the integration with ROS, also robot operating system. So when we have all the information stored in our topological maps, which is created by BIRS, we can create a hypergraph of the topological map. This hypergraph is created by nodes and edges. The nodes are the IFC spaces, and the edges are IFC doors, and all the attributes are extracted by BIRS. As you can see, these nodes are building spaces or building rooms that we extracted from IFC, and then we assign weights to each transition from one node to the other one. How we do it? For each node, we have different weights, such as weight of material, weight of area, weight of scanning age, and a weight of hazard or safety to the robot and construction workers. Also, we have for the weight of edges, we assign the door swing weights to edges, and the total weight for the transition from one node to the other one is the sum of nodes and edges weights. So for example, in this case, if the robot wants to go from node V1 to V2, you can see that, for example, in this case, we have an overall weight of 18, so that the robot would understand that which path is better. Does it have to go from V1 to V2 and then V3, or it needs to go through V4 then to V3? And all this information is provided by BIM and then integrated with ROS. I would like to highlight that this kind of semantic path planning is not necessarily the shortest path. It's the optimal path for the robot to collect more information of the building, to consider the safety of the workers and the robot itself, and also the time of transition, and also the material. Because some materials, such as glass, are invisible to the robot sensors. So, for example, a glass is invisible to a laser scan, so that the robot cannot see what a glass as an obstacle, but we covered and bridged those information from BIM, so that the robot can have a very good understanding of what's going on around it. As you can see, these are different criteria for assigning weights for each weight. For example, for wall material, we have invisible wall material and any other wall material. So in this case, we assign high and low. And for space area, we have three divisions: less than 50 square meter, between 50 and 100 square meter, and more than 100 square meter. So we assign low, medium, and high respectively. And again, the same goes for scanning age. And I would like to highlight here that the safety was very important for the robot navigation. So for any hazard that comes on the robot's path, we assign a very high value, so that we want the robot to avoid that area. And also for the door swing, as it is
Sina, can you hear me? Can you talk again? Oh, I think you're back. Yeah, you're back. We just lost you for like 20, maximum 15 seconds.
Oh, I'm sorry, my connection should be unstable.
Go ahead.
So the algorithm that we develop it provides a hypergraph, and then the hypergraph is comprised of the tail room and head room, which are the nodes. And the hyperedges are the doors and the transition between each each nodes, so that the total path weight is the hyperedge total weight. So that when we provide all this information automatically to the algorithm outputs a list of nodes and hyperedges, and so that it is kind of like a high-level path planner for the robot that contains BIM information. After that, the algorithm provides coordinates for the robot navigation from nodes and hyperedges, and also the total weight is the number for the robot. So if we have two paths, the path with lowest weight is the most optimal path for the robot to navigate, so that it can be the shortest path, but it is not necessarily the shortest path. Here is the system overview and also the robotic platform that we use. We use several sensors integrated with the robot, as you can see, the laser scans, RGB cameras, depth camera, tracking cameras, and also IMU and the wheel encoders. So for the system overview, the robot takes the information from LiDAR and the tracking camera and put them into the localization mode. The localization mode also gets the information from a BIRS database, which contains the BIM information. And as you can see, the higher part of this graph is the high-level path planner based on BIMIFC information, and the low-level path planner is what the robot uses to transit from one point to the other one. And the transition from that is calculated, and we use A* path planner to find the shortest path within the optimal path. And after that, all this information is provided to the control node, and the control node sends the velocity commands to the motors to navigate from one node to the other. Here, since we wanted this,
you have 1 minute. If you're able to complete soon, that would be great.
Sure. We wanted this platform to be intuitive for the construction stakeholders, so that we developed a semantic graphical user interface. As you can see on the top left, we provide destination selection, and the algorithm provides a path for the robot. Then we have the attributes of the selected room. In the middle is the map of the environment and the real-time robot pose, so that the user can supervise where the robot is and what the robot is doing. And also we can reconfigure all the weights for the different weights. I would like to mention that my colleague Rafael Gomes Braga is extending this work to provide with a user study to provide more information and better ease of use for the construction stakeholders. And at the end, I would like to talk about the field deployment. So we pick for the first experiment, since there was no construction activities here, the algorithm generated the path 1, as you can see on the top, on the bottom, the blue line. So it has the lowest total weight among the other alternatives. But since there was a construction activity and it provided high weight to the edge, the algorithm automatically generated another path so that the robot could navigate from another space and reach out to the end. And the main objectives were to test the effectiveness of the semantic path planner and test how changes in the building can affect the final path is generated by the algorithm. I would like to thank you for your attention.
Great, thank you very much. I see you are actually just about finished, so that was excellent. I'm just posted on the chat if there are any questions from the audience. Nothing is coming just yet. I have one actually. Oh, there is Chen Fang. Thank you again, Chen. Thank you for the nice talk. How to systematically set the weights to ensure the planned path will respect all hard constraints, especially for a complex job site? Is it based on trial and error?
The first study was using another paper that also is mentioned in our paper published there, so that we use that experiment to provide the initial weights for the robot. And after that, working with the construction stakeholders, we identified different weights for each path. The thing is, through this semantical graphical user interface, you can reconfigure everything here in this user GUI or user interface, so that whenever you can kind of like customize it for your application. So so that, for example, if there is something more important for you, you can just configure it here, and the robot can navigate through those spaces and collect data.
Okay, thank you. I have a question. You mentioned the ontology that you guys worked on. Is the ontology published anywhere for people to use or maybe contribute to, etc.?
Yes, the ontology is published, and I provided the detailed information at the bottom. If you can.
But this is a paper publication, but it's not a web ontology. Like, it's not on GitHub or something, like something that people can contribute to, or is it?
No, it's not on GitHub yet, but we have the intention, and then we can share it on GitHub. Because
my experience, and it's not criticism, it's just everybody's working somehow on ontologies one way or the others, some more than others. But my experience is like it's been really hard to find out what ontologies already exist and where and how you make use of them, etc. I think this is quite an area where the construction sector, I mean, the people working in automation robotics in construction, we need to somehow take a coherent approach so that we don't try to reinvent the wheel and are able to identify when ontologies already exist and can simply be reused. I think that's an interesting issue. Okay, I don't have any other question right now, but obviously monitor the chat. There might be more questions. But once again, Sina, thank you very much for your presentation and for the work that you and your colleagues have done.
Thank you so much.
Okay, thank you.